Okay, so before the break, we started discussing about the idea of learning basis functions, right? Like, so instead of handcrafting these basis functions, like, so we can actually learn these basis functions simultaneously with the parameters of the classifier, and that is representation learning. And we can do representation learning with like a multi-layered neural network, like what we are seeing in the slide, right? So this is where we stopped. So now we are going to make things more precise and like in a mathematical way. Okay, so now let's say we have a prediction problem. Okay, actually it could be regression or classification, it doesn't matter. Okay, now the input is given by some x, let's say it's d-dimensional. Okay, and my output is given by t, which is some k-dimensional. Now it could be a one-hot k vector, in which case it's a classification problem, or it could just be k real valued outputs. Okay, it doesn't really matter. Okay, now an MLP or multi-layer perceptron is defined as follows. So first we are going to take this x and multiply that with the weights of the basis function. Okay, so it's going to become W1 x plus B1. Okay, I'm using the squared numbers for layers. So this is the first layer parameters. So I'm going to call this as some a of x, and my h of x is given by g of a of x. Okay, so h is my hidden layer. So the output of the hidden layer, which is basically the basis function, is given by some linear function a of x followed by some non-linear function g. Okay, because we know that the basis function has to be non-linear, right? So it's a non-linear function. Now this a of x, right? So this has a name in the literature. This is called pre-activation. Okay, and this non-linear function g is called activation function. So whatever you compute before applying activation is the pre-activation. It is just a linear layer followed by the non-linear activation function. Is that clear? So that is my h of x. So h of x is actually the phi function, the learned basis function. Okay, so this is what we have been previously calling as phi of x. Okay, now once you have the h, then you can pass h as input to my classifier. The output y is some f of x, which is some function O of W2 transpose h of x plus B2. Okay, where the W2 and B2 are the weights of the second layer, the hidden to output layer. And O that you're seeing here is the output activation function. Is that clear? Okay, now this is my model. So compare this to something like linear regression model. So what would be the equation for linear regression model? Anybody? What is the equation for linear regression model? Yeah. Yeah, just y is equal to W transpose x plus B if you want the bias, right? And similarly, if you want to do logistic regression, it is basically y is equal to sigma of W transpose x plus B, right? On the other hand, this MLP is implemented by this set of equations. Like, so you first compute a of x, then you compute h of x, then you compute the output y. Is that clear? Now, can somebody tell me what are the parameters of this MLP? So what are all the parameters of this MLP? Well, it's not that hard. Yeah. So it's W1 B1 and W2 B2, right? we have to learn all these parameters in the data. Once you learn the parameters, then you have your network. Is that clear? Now, there is actually a very concise graphical representation for this set of equations. Okay, so we would often start doing that as we get into more and more complex architectures. So your input X is this, it's a bunch of input units. Then you pass it through W1, okay, and you get H of X. Okay, so I'm ignoring the bias here, but W1 also has the bias internally. Okay, then you pass it through W2, then you get output Y. Is that clear? Now, let's go back here. Now, it is very, very important that G is a nonlinear function. Now, can somebody tell me what would happen if G is a linear function? Yeah? Yes. If you compose linear functions, you get linear function, right? Like the whole model is going to be a simple, it will just reduce or collapse to the simple linear model. There is no use in having such an architecture if G is linear. Okay. Now, a more precise way of saying that is your Y is going to be W2 times H of X, right? Like if it is linear, then this is just W1X plus B1 plus B2, right? If there is no G here, okay, so you need a G function here to make things nonlinear. If you don't have the G function, then this is actually equivalent to Y is equal to WX plus B for some W and B, okay? So there is no use in these projections, like, so you're not gaining anything. Okay, so it is important that G is a nonlinear function. Now, it is also important that G is a differentiable function. Okay, why? Because let's say I want to compute the gradient with respect to W1. So how would you compute the gradient with respect to W1, right? Like, so Y is a function of H of X. H of X is a function of G. G is a function of W1. So there is actually a chain rule involved in computing this gradient. Now, for this chain rule to complete, you should be able to differentiate with respect to G. So if G is a non-differentiable function, then you cannot compute gradients. Is that clear? Now, this means there are not many possibilities of G function. Okay, there are only very few possibilities. So we are going to see some examples today. Okay, so the first activation function that one could use is the idea of sigmoid functions, which we have already seen before, right? So Y of A, sorry, G of A is given by sigma of A, which means 1 by 1 plus e power minus A. Okay, so sigmoid would look something like this. Okay, it has the range of 0 to 1. And there are, like, we have already seen the properties of sigmoid before, right? Like, so this is always positive. Okay, and also it is bounded, so it is bounded between 0 and 1, and it is also strictly increasing. Is that clear? So this is one example for nonlinearity. Now you could also use tan H nonlinearity. Okay, now tan H is given by this formula, since G of A is equal to tan H of A, which is given by e power 2A minus 1 by e power 2A plus 1. Okay, so the tan H function actually looks very much like sigmoid, except for the fact that it is from minus 1 to 1. So it can be both positive and negative. It is bounded between minus 1 to 1. It is also strictly increasing. Is that clear? So we will see more activation functions in the future, but for now we can get started with sigmoid and tan H. Okay. Now what about the output activation? Right. So this O function. So what kind of output activation functions we can use? So if you are doing regression problem, right, then you don't need any activation function. because the output of regression is just wx plus b, right? Like you don't need like a sigma or tan h or anything, right? So in that cases, you can use what is called as identity function, which is really simple, like no change. Okay, so this is if you are using if you're using regression. Okay, now you can either use sigmoid function if you're doing classification where the output needs to be between 0 and 1. Like for example, let's say you're doing a binary classification, then your output is going to be probability of class 1, right? So you can do that with sigmoid function. Now, if you have a multi-class problem, then you can use a softmax function. Okay, for multi-class probability distribution. So we have already seen the softmax function. Is that clear? Any questions about activation functions? Okay, so now I keep telling you that this is a nonlinear model, right? So how would the decision boundary of neural network look like? Okay, now it is going to be complicated, just like how we have seen the decision boundary for k nearest neighbor. Okay, I want to give some examples. Okay, so here are some examples. Now let's first start with the first example. Okay, so in the first example, you see you pass the input and there are 2 units here. Maybe I'll highlight it. There are 2 units here, right? Maybe let me use a better color. Okay, there are these 2 units here, right? Now these 2 units are simple step functions. Okay, so you see the first step function is this, and the second step function is this. Okay, they can only do linear decision boundary. However, the beauty of this network connection is when you combine these 2 linear decision boundaries, okay, the intersection is a non-linear decision boundary. Is that clear? Now, similarly, I can take a bunch of sigmoids, which are all having this curved decision surfaces, and put these things together. The intersection could be a blob like this, right? And when you combine many such nonlinear classifiers, like nonlinear basis functions, like our activation functions, you could get as complex decision boundary like this. Here you see that there is region 2, there is region 1, and within the class 1, like there is one region for region 2, and within that there is another region for region 1. Right? So you can have, if you think about it, like you can have these kind of complex things with k nearest neighbors, right? Like because it is a nonlinear classifier as well. So similarly, like you can have really nonlinear like decision functions here. Okay. Now we had this discussion for k nearest neighbor. We discussed in detail that k nearest neighbor is a universal function approximator, right? Like so you can model any function with k nearest neighbor, right? Similarly, there is also similar characterization for neural networks. Okay, so there is this famous universal approximation theorem, okay, which was due to Hornig in 1991. Okay, I will state the theorem. We will not prove it, of course. Like so, we are just going to discuss the implications of the theorem. Okay, the theorem is this: a single layer or a single hidden layer neural network, okay, with a linear output unit, okay, can approximate any continuous function, okay, well, given enough hidden units. Okay, so this simple MLP architecture that we have seen, right? Like where there's an input layer, hidden layer, and output layer. You take such an architecture with a linear output unit, okay? So this architecture or a model can approximate any continuous function, okay, given enough number of basis functions of the hidden units. Okay. Now, the big catch in this particular universal approximation theorem is that this holds only given enough hidden units. Now, if you compute the amount of hidden units required for the problem, it actually grows exponentially with respect to the problem complexity. Okay. So as the complexity of the problem increases, you need exponential number of hidden units. Okay. So, which means that this is not a very useful theorem because, like, well, it tells us that you can do it, but it doesn't tell you how to do it, right? Like, so for example, even if you have exponential number of hidden units, this theorem does not give you an algorithm to find those optimal parameters, right? Like, so this is more like an existential theorem, right? Like, so existential theorems are always not that useful. Like, so it just tells you that, yes, you can do it, but how do you do it? Like, we don't know it. Okay, so is that clear? Any questions so far? Okay, now we need some practical way of solving this issue, right? Like, so, like, of course we cannot have exponential number of units for the problem. Like, so it's going to grow too much, and then like maybe gradient descent cannot find the solution like with this exponential number of hidden units, right? Like, so how do we solve this issue? So like an obvious next step here is, well, maybe it's not that obvious, but the intuitive next step here is, let's say this is my network, this is my, so this size of this hidden layer has to grow as the complexity of the problem increases, right? Like, so one possible alternative, which is practically very successful, is instead of widening the network, instead of widening this basis function, how about I learn a series of nonlinear basis functions? Okay. Now this is an extreme form of nonlinearity, because what I'm going to do is I'm going to take x. Okay. I'm going to learn my first basis function h1. Now I'm going to take this as input and do another nonlinear projection h2. Okay. And I'm going to take this as input and do another nonlinear projection h3. Then I make the final projection. Is that clear? So when you take already nonlinear representation and do another nonlinearity, you kind of get that exponential power, but with much more tractable setup, right? So I'm going to give you a cartoon illustration of how this is useful. Okay, there is nowhere. I'm not sure if this would really happen. Like, but here is a cartoon illustration. Like, so imagine you start with a problem like this. Okay. Now this is a nonlinear problem, right? Like, it is not linearly separable, right? Now the hope is each and every nonlinear projection is going to make the problem simpler and simpler and simpler. Okay. So for example, the first transformation might move things like this. Okay. The second transformation can actually move things like this. Okay. And maybe the third transformation is going to move things like this, so that it eventually becomes easier to draw a linear classifier. Is that clear? So now what we are going to do is, instead of just considering one projection layer, we are going to consider many projection layers. Okay, but the equations are simple. So just like how we had W1, B1, we are going to have W1, B1 for first layer, W2, B2 for second layer, W3, B3 for second layer, and so on. Okay. Now I can generalize this whole idea into a L layer neural network. Okay. So for each layer K, my pre-activation is given by AK of X, which is basically BK plus wk times the input from the previous layer, so hk minus 1 of x. Okay, so we're going to assume h0 of x to be x. So you start with x, when you do h1 of x multiplied by w1, so w2, which gives you the a2, right? So, and you have hk of x to be equal to g of ak of x. Okay, and finally the output hl plus 1 of x is going to be the output function of al plus 1 of x. This is my function f of x. Is that clear? So we still haven't seen how to learn these parameters. Okay, so we are still talking about like how to construct these neural networks. Okay, yeah.
The L is only the number of layers between the input and output, or does it include the input output?
Well, it is just the number of hidden layers. But this is just convention. You can call it in different way as well. It doesn't matter. There is no standard here.
Yeah.
So when I say L layer, I mean L hidden layer neural network. Okay. Is that clear? Okay. So now we can finally talk about learning. Okay. So we will see how to learn the parameters of the neural network. Okay. So to do that, we need a specific instantiation of the problem, right? Like, so we are going to consider an MLP with n input units and m output units. Okay, you can have any number of hidden units, it doesn't matter. Okay, the algorithm, so the model is going to look something like this. H is given by g of w1 transpose x plus b1. Okay, and y is given by o of w2 transpose x plus b2. Okay, where g is my activation function for the hidden layer, o is the activation function for the output layer, w1 and b1 are the projection layer parameters, and w2 and b2 are the classifier parameters. Is that clear? Now, we are going to consider a training data set. Okay, which is going to have a bunch of examples. Let's just say we have p different examples. Okay, well, I'm sorry, I'm switching from capital N to capital P for the rest of the lecture. So, well, this comes from a different source. Like I did not translate it to N. I don't want to do the translation on live, so maybe I'll make mistakes. So let's just from now on consider capital P to be the number of examples. Okay, so where capital P is the number of examples in the search. Okay, now we're going to consider a simple least square kind of error function. Okay, so our error function is going to be 1/2 summation I is equal to 1 to capital P yi minus t of I the whole square. Is that clear? Now we are going to do gradient descent to learn these parameters W, B, W's and B's. Okay. Now, first of all, this is a very simple process. Like, I think by this time we know how to do. By this time we know how to compute gradients and set up gradient descent for any model, right? So, like for example, like if I have to do this, so what do I need? Like let's do something now. Like let me take this whole thing to the next page. Okay, so now let us do, for example, the gradient for W2 to begin with. So what would be dou E by dou W2? Right? So E is not a function of W2. However, E is a function of Y and Y is a function of W2, right? So I can actually apply chain rule of differentiation here. So dou E by dou W2 is going to be dou E by dou Y I, okay, or dou Y, let's just call it dou Y to be simple. Dou E by dou Y by dou O, okay, dou O by dou W2. Okay, I can actually write these differentiations. I'll get a formula here. We are not interested in that formula, so we are not going to expand this. Okay. Similarly, if you want to do dou E by dou W1, what would you do? Can somebody tell me what is dou E by dou W1? So what is the chain rule? Yeah.
It's the same chain, but you only change E W1 in the last. E W2 to E W1 in the last.
Okay, dou E by dou W,
Oh, yes, we have to.
dou Y by dou O. Okay.
And we have
Oh, I did a mistake. So this is H. Sorry.
you have to do it with the O to the H.
O to the H, H to the G, G to the thing, right? So dou O by dou H, dou H by dou G by dou W1. Is that right?
Yeah.
Okay. Now, it is kind of easy and straightforward to just compute gradients here if you use gradient like chain rule, right? Like so. Now it is possible to use chain rule here because things are differentiable function of each of them, like it is a continuous function. So you can just use chain rule here, right? Now, if you want to implement this chain rule, like a naive implementation of this chain rule is going to do a lot of redundant computations. Okay. Now, there exists an efficient method to implement this chain rule, like which is going to do the least possible computation as possible and hence be more efficient in computing the gradients. Okay. Now that is the idea of backpropagation. Okay. So we will start discussing about backpropagation today, but we will also continue it next week, which means you have to really refresh your mind and like memory before you come for the next lecture. But backpropagation is essentially an efficient way of implementing chain rule, okay, by using dynamic programming. Okay. Now we are going to see how to do that. But before that, remember that our learning algorithm is through gradient descent. Okay. So we are going to do gradient descent to train the neural networks. The backpropagation is not a learning algorithm. So backpropagation is just an efficient implementation to compute the gradients to be used for our learning algorithm, which is gradient descent. Okay, is that clear? Just to make things clear. Okay, now how am I going to do this, right? So to do that, we are going to consider, this is what we are going to do. We are going to bring everything to the graph structure that we have, okay, so that we can actually compute the gradient within the graph. If you compute the gradient within the graph, I'll show you that it is going to be much more efficient to do that. Okay, so how am I going to do that? So let us say I have a bunch of inputs. We are going to consider an ith example. Okay, so this ith example has, let's say these are the inputs. Okay, these are my input units. Okay, now for backpropagation to work, it doesn't really matter that you have to have this MLP structure. Okay, you can have any structure you want. You can have as many connections going to any unit as you want. So we don't worry about the connection. So we are just going to assume that there is some multiple layer architecture. Okay, this architecture is going to give you the output. Okay, so which is basically y1i, y2i to ymi. Is that clear? Now I'm going to take this output and compute my error as another node in the graph. Okay, So the error for the first term is given by 1 over 2 y1i minus t1i the whole square, right? This is the error, but just for the first output. Okay. Similarly, the error for the second output is given by 1 over 2 y2 of I minus t2 of I the whole square. Similarly, for the last unit, it's 1 over 2 ym of I minus tm of I the whole square. Okay. Now, my actual error is a sum of all these things, right? So I'm going to do a sum of all these things. Okay. So this sum is going to give me the error for the ith example. Is that clear? Now, so what have I done so far, right? Like, so I took my neural network, which basically takes these x as input and give me a bunch of y. Okay. Then usually you'll take the output and then you compute the loss separately, right? Now I'm kind of bringing the loss within my network. Right? So I'm creating units for loss. These are my loss units. Like for each of these, like I have separate loss and then I sum them together. Is that clear? Now, this particular network that I have will take input x and give me the error directly. It is not giving me the predictions. The predictions are somewhere in between. This is the prediction, right? But this network is giving me the final error given my input x. Is that clear? Now, this is for one example, right? Let's say I have 10 examples. Then I'll have 10 such graphs. Okay, so graph 1, which is giving me E1. Okay, then another graph 2, which is giving me E2. Okay, let's say I have 10 examples, then I'll get up to E10. And then I will sum all these things. That will give me the final total error from this data set. Is that clear? Now, once I have everything represented as a graph, okay, now I'm going to show you a method to compute the gradient directly from the graph by using dynamic programming. Okay, now, so our goal is actually to compute del E, which is dou E by dou W1, dou E by dou W2, dou E by dou WL, where L is the total number of parameters in this neural network. Okay, so once I compute these gradients, then I can update each Wi with some del Wi, which is minus alpha times dou E by dou Wi. Okay, so I can update Wi is equal to Wi minus alpha times dou E by dou Wi. Okay, is that clear? Now, the whole learning problem actually reduces to the question of calculating the gradient of a network function with respect to its weights. I have a network or a graph, and I want to calculate the gradient with respect to the weights. Is that clear? Now, our goal here is to find a method for efficiently calculating the gradient of a one-dimensional network function according to weights of the network. Okay, so how do I do that? So to do that, I'm going to introduce what I'll call as B diagrams. Okay, also known as backpropagation diagram. Okay, now each circle or the node that you are seeing in the neural network, right? So we are going to represent it as follows. We're going to divide it into two parts. Okay, so the first part is the right part is the function f, whatever function that the unit is representing, and the left part is f dash, the differentiation of the function. Okay, now the right part is basically the primitive function associated with the node, and f dash is the derivative. Is that clear? Now let's say I have a wx plus b, like g of wx plus b. Okay, or let's say sigmoid of wx plus b. Now I can actually split this into two parts. The first node doing the integration, like doing all the addition in the linear function, and the second node doing the different, like doing the activation function. Okay, so I can actually take all the things and do the summation, which is what wx will do. Then I pass it through the sigmoid function. Okay, so this is to represent sigma of wx plus b. Okay, now for sigmoid we have sigma dash. You already know how to compute. Now when you add things, a bunch of things, differentiation with respect to any of the individual item is just 1. Is that clear? Any question? Okay, now here is the algorithm. Okay, my backpropagation algorithm is going to work in 2 stages. So you're going to have a feed forward stage and a backprop stage. Is that clear? So in the feed forward stage, every unit will take its input, compute the function of the unit, and compute the differentiation of the unit. So every unit is going to compute both the function and its differentiation. It is going to store them and pass the function to the next unit. Is that clear? Now, once you finish this whole process, this is called feed forward because you start with x, you pass the input, make the computations, you pass the input, make the computations, and so on. Okay. Once you finish this, you're going to go to the backprop stage. Okay. In the backprop stage, they're going to consider 3 cases. Okay. So first, case 1 is function composition. Let us say I have a function which is a function of another function, f of g of x. Let us consider f of g of x. Okay, so how would you represent this using the B diagram? Like, so you take x, you'll first pass the x to the g function, right? So then you will pass this to the f function, and you get the output, right? So when you differentiate the whole thing, at here you get g dash, here you get f dash, right? Now, let us see how the feed forward stage will work. Like, so in the feed forward stage, you get x, okay, and from x, once you reach here, you get g of x, right? From here, once you reach f, f takes g of x as input, so you get f of g of x. Is that clear? So the feed forward stage, like you just pass the x to the first function, it gives you g of x. You pass it to the next function, it gives you f of g of x. Okay. Now, here is a neat way to compute the gradient with respect to x. Okay, so I'm interested in computing. Let's say this is y. Okay, I'm interested in computing dou y by dou x. Okay, can somebody tell me what is dou y by dou x by chain rule? So what is dou y by dou x? Y is a function of f, which is a function of g, which is a function of x. So what would be the answer? Yeah.
It's df dg minus dg dx.
Okay. Yeah. So it's basically f dash. First you differentiate f, right? So then you differentiate with respect to g. F dash multiplied by g dash, right? This is what the chain rule gives us. Now here is an easy way to compute this by using this diagram. Okay, so what you have to do is you just put 1 here. Now just like how we multiplied all the right part of the unit for computing the feed forward, we are going to multiply all the left parts. Okay, so you multiply 1 with f dash. What do you get? You get f dash, right? Now you take this f dash and multiply with this, you get g dash. So if you go backward with 1 in the beginning, you get f dash g dash, which is exactly what you want. Is that clear? So if you have this function composition, now you can actually compute the gradient by using this B diagram. Now, similarly, let's actually do the 2 more cases. Like the case 2 is when you have function addition. For example, when you do the W transpose X, right? Like if you expand W transpose X, it's a bunch of W1X1, W2X2, W3X3. You're adding a bunch of things. So when you have addition, let's just take let's just say my Y is equal to F1 of X plus F2 of X. Okay. So how would I draw B diagram for this? So I'll take the X and I pass the X to 2 functions, F1 function and F2 function. Okay. Now I have to add them together, right? So I have an addition function, and this addition gives me the output, F1 of X plus F2 of X. Okay. We know that when you have addition, the left-hand side, the differentiation is 1. For F1, the differentiation is F1 dash. For F2, the differentiation is F2 dash. Right? So now how would the forward prop work? So you will start with X. You'll pass X to F1, so you get F1 of X. You pass X to F2, you get F2 of X. There is F1 of X and F2 of X. You add them together, so that is what the function is. Right? Now, before even computing the chain rule, let us try to do our backprop trick. Okay, so I will put a number 1 here. Okay, now I have to compute gradients in 2 different paths now. Okay, and whenever there is something like this, like you are adding them together. Okay, so now you see I put a 1 here, I multiply this 1 with this 1, I still have 1. Then I multiply it with F1 dash, so I get a F1 dash coming here, right? Similarly, I take this 1 and this 1, multiply it, and I come to this, there is F2 dash, and I have a F2 dash coming here. Whenever there is a connector, you add them together, so you get F1 dash plus F2 dash. Okay, now, if you compute dou y by dou f, dou y by dou x, it is basically F1 dash of X plus F2 dash of X, right? It's the same function. So now if you have additions, you can actually compute the gradients easily. Finally, there is one more case, which is the idea of weighted edges. Okay. Now let's say I have some input X, which passes through a weight W to WX. Okay. Now, how do I compute the backprop? So whenever you have weights in your edges, whatever gradient that is coming in will be multiplied by the weight. That's it. Okay. So it is really simple. Like when you are doing the backward phase, you will put a 1 here. So 1 will be multiplied by W. So you get the output to be W. Okay. So we already know that if Y is equal to WX, what is dou Y by dou X? What is it? Just W, right? Which is what we compute here. Is that clear? Okay. So now we can actually put together the whole thing into an algorithm. Okay. So the backpropagation algorithm so is going to take some input X and they're going to compute some function F. Okay. And we are going to compute dou F by dou X. Okay. Remember, we are still computing the gradient with respect to the input, but what we really care is gradient with respect to the weights, right? So we will come to that probably next week. But for now, we have an algorithm to compute dou f by dou x in an efficient way. Okay, so the algorithm works like this. There are two stages. Okay, the first stage is called feed forward stage, which is really take the input, pass it through the network. Okay, now if you have this extended network which has the error coming out, you will pass it step by step. You finally reach the error. So that is your feed forward computation. So when you are doing the feed forward computation, you are storing not just the output of the unit, but also differentiation with respect to the unit. For example, if you have a sigma unit, you will compute sigma in the right side, sigma into 1 minus sigma in the left side. If you have an addition unit, you will compute the addition in the right side, you will put 1 in the left side. Is that clear? So it is easy to do this thing, right? Like so. Now in the backprop stage, we will always put a 1 in the n, okay, and we will multiply this 1 with the left hand side of the unit, okay, and whenever there are two parts, we will add both the parts together when they merge, okay, and whenever there is a weight, we will rescale by the weight. You go all the way from the back, all the way back from output to the input, you will get dou f by dou x. Is that clear? So any question about the idea? Yeah. Okay, well, that's a good question. The question is, do we need to do this back propagation step after each data point, right? Like so. Now, a naive way of implementing this is by using back propagation for every data point. So however, like as we will see in the next week, so we can actually batch these things. You can use a mini batch of examples and compute the gradient with respect to the mini batch of example directly. Okay, so the nice thing is every operation that we are going to see in the backpropagation algorithm in detail next week, they all extend from vector to matrix, like when you have a mini batch. Okay, so it is possible to do the mini batch computation, but we will talk about it next week. Okay, so any other question? So I think we should, well, I very much wanted to not finish in the middle, but we have to stop here. So we will, okay, so far we have only seen how to compute gradient with respect to input x, right? So the most interesting thing is how to compute the gradient with respect to the weights. So then we have the algorithm, right? So we're going to do that. We're going to do that next week. And we will also talk about how to train very deep neural networks. And you have many, many layers. Like, so what are the problems that you would face and how to solve those issues and so on. And we will, okay, and we will also talk about like other advanced concepts. So any questions about neural networks? Yeah.
Just conceptually, the weights on each of these in the graph, are those the values in the W matrix?
Yes.
Okay.
Weights in the edges are basically the values of the W matrix. Any other questions? Okay, so then probably we will stop here and I'll see you next week.